name is Blaine, and this is my sock. Today I'm going to be talking about exponentials and logarithms. So let's start with exponentials. An exponential is when you have a number, say 2, and you multiply that number by itself a certain amount of times. And that amount of times is based on this little number you stick in the superscript up here. So let's say 2 to the power of 3. So this is equivalent to 2 times 2 times 2, which is also equivalent to 8. And so you can get crazy with exponents. So you can say, oh, let's raise 2 to the power of 15. So that would be equivalent to 2 times 2 times 3, which is equivalent to, 1 second. 32,768. And let's try to smash some algebra into this. Alright, get in there, sock. Let's apply this, let's algebra this up. So let's get a thing. Let's say, oh, that's ugly. X is equal to 5 to the power of 3. Now, this is essentially equivalent to 5 times 5 times 5, which is equal to 125. Alright, now let's try to swap the x around and put it in different places. 125 is equal to x to the power of 3. Here's some cool algebra stuff to move an exponent to the other side. Similar to how you would, when you're dividing something, you shove it in the denominator. You do the same thing, except that you stick it in the exponent denominator. So this is actually equivalent to 125 to the power of 1/3. What? And some bozo decided they're like, yeah, let's make up a new notation for this. Let's call it roots. So, if you want to be annoying, then you can say 125 to the cube root. So that's very annoying, so don't do that. Yeah, let's move on. Let's try throwing the x somewhere else now. Yeah, so that's easily solvable. You can whack that in your calculator. But as you move along, 125 is equal to 5 to the power of x. Then we run into something new. Here is where we would use logarithms. Because besides just like counting, multiplying 5 by itself a bunch of times is really hard. So that's where logarithms come in. Hello! I brought colored markers. So now let's learn how to convert this into a logarithmic form. To do that, I'm just going to rewrite it here with colors. Alright, so there we have delegated a color for each of our segments. Here we have our base, which is in red. We have our exponent, which is in green, and then we have the answer, the product of the exponent. So to convert it into logarithmic form, you're going to turn it into this. We're going to say log, and then base 5. So the 5 is going to come down here to the little subscript. Log base 5 of 125 is equal to x. There we go. Now we are solving for the exponent. That is lovely, except that you can't really ram this in your calculator, because on your calculator all you have is log to the base 10. Here we have log base 5, that's a problem. However, there is a log rule that we can use to change the base to whatever we want. It goes like this. X is equal to log, and you can select your base. We're going to go with 10. Log 10. And if there is no base, then it is implied that it is log base 10. So even if we were this, then it would be log base 10 anyway. Yeah, same thing. So, we are going to bring the power down here, 125, and then we are going to bring the base down here, 5. If we shove that into our calculator, oh, we get 3! And, so that's 3, which we also determined up here. So therefore, we are right. Now that we've learned how to solve logarithms, let's talk about the logarithmic scale. Now traditionally we're familiar with the linear scale, so I'm just going to draw both of them and compare the two. Okay, 2 lines. Okay, so with these linear scale, you go up by adding increments, and you can select an increment size. So we're going to select an increment size of 2. So we're going to go +2, +2. Alright. So just to Right, that is going to turn into 2. Alright, so there we have our thing. So here we have our increment size. We're also going to look at the increment number. So this is increment 1, increment 2, increment 3, 4, 5, 6, 7, 8. Now let's see how all of these numbers, the increment size, and the final thing, how they all smash up together into a function. And then we're going to graph it. So throw down this big square. And so this is going to be our x-axis, and this is going to be our y-axis. And we're going to say that our x-axis is the increment number, and the y-axis is going to be this big thing on top. So these numbers up here would be 2, and then times 2 is 4, times 2 is 8, times 2 is 16, 2, 64, 128, and 256. Alright, similar to the top, we're going to turn this into a function and graph it. So the function for this is y, we're going to call that y, and it's going to be x. And it's going to be y is equal to 2, and it's this number times whatever number of increments it is, 2 to the power of x. So it's an exponent variable again. That's where you need logarithms to solve. That's why it's called the log scale. But you can still graph it. So we are going to graph it. So this is going to be the x-axis, the y-axis, which is the x, that's x, and y is over there. It's going to go up to 8. 1, 2, 3, 4, 5, 6, 7, 8. It's going to go up to 256. That's a lot bigger than the last one. 256. I was just kidding. You know what, to make things easy, I'm going to go straight up to 300. And that's going to be 150. And that's going to be 75. And 100. Okay. 225. Alright, so there's our graph. So, when x is equal to 1, y is equal to 2, which is just like right there. When x is equal to 2, y is equal to 4, it's still like 9. When y is equal to 3, y is equal to 8, 9. X is equal to 4, y is equal to 16. Okay, x is equal to 5, y is equal to 32. Hey, 32, that's like half of 75 almost. So that's going to go right there. And x is equal to 5, y is equal to 64, that's like kind of below 75. X is equal to 7, y is equal to 178. 128. That is somewhere around here. And then finally, when x is equal to 8, y is equal to 256. That's a big jump there. It turns into a big, happy, not linear graph. Compare the two. If you're looking at this and you decided, hey, where's 100 on this graph? You want to figure out what increment, at what increment would you find 100? So it's somewhere between 64 and 128. So it's 6 point something. I'm gonna draw a big oval right here. It's so it's 6 point something. But you want to get more precise. So when y is equal to 100, then 2 to the power of what is equal to 100. Now to solve for this exponent, we're gonna have to convert this into the logarithmic form, just like we learned just recently. So that is going to look like x is equal to log base 2 of 100. That's our equation, and we cannot smack that into our calculator yet because log base 2 is not computable. Luckily, we have the log change base law, which looks like this. X is equal to log of your power over the log of your base. So with this you can convert the base to whatever you want. So we are turning it into log base 10. So now that it's in log base 10, we can shove it all into our calculator. I'm gonna do that. So 100. Oh, that's 1,000. 6.64. So x is equal to 6.64. Yeah. So that means that 100 up here is at 6.64, which is approximately, if you look at these increments, 6.5, 6.64. Right there, that's where you find 100. So that is how you use the logarithmic scale. Now, the log scale is very exciting, and it occurs in many natural phenomena. Specifically today I'm going to be talking about sound frequencies and note correlations. So here I have drawn out the notes C up to high D and the corresponding frequencies below them. And let's assume that it is on a linear scale, except that something wonky's going on here, because, well, I guess it's hard to see. But the difference between low C and low B is 294 minus 262 is 32. So that's the interval between C and D. But if you look at the interval between these C and D's, high C and high D, 587 minus 524 is actually 64. So what? The increments have doubled. That's evidence against it being a linear scale. Furthermore, see this high C, 524. Low C is 262. This is actually double the low C. So high C is low C times 2, and it continues as you go up the octaves. And so the next C above this C would actually be 1048. So yeah, maybe it's not a linear scale. Just to push this further, just to prove this, I'm going to try to draw this out on a linear scale. Okay? So, from the end here, the maximum is going to be 1048. 1048 hertz. And this is high C. It's the C that's up here. As we discussed earlier, half of this would be the C below it, right there. So, 587 times 2. So this times 2 is going to be, 524, wrong number. Times 2 is 1048. That is where the next C goes. C below that is going to be half as well. So, smack that in half. 262 C. See the pattern here? Half of that is the next C, 131. So here, we have our linear graph depicting the octaves and their correlated frequencies. So you have to remember here that between here, we have a full scale of da 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 da. So here you also have a D note and an E and an F and a G and an A and a B. So it shrinks as you go along the scale. So it's quite obviously not a linear scale. And just to prove this further, have a look at this very nice bass guitar. So here I have a bass guitar, but pianos. Crap. Pianos. Okay, I can do this. Pianos have lied to us and have made us believe that these notes, as they ascend, are just all linearly related due to the fact that all the keys are just the same width and it just goes up with frequencies, who cares, whatever. It totally blocks it out of your mind. But if you look at a guitar, you can see that the frets progressively get narrower as you go up the neck. And that shows you how the notes, though going straight up, frequencies aren't linearly related to them, and they shrink. And another point that we have is you see how as you go up an octave, the frequency doubles. You can achieve that on a stringed instrument by chopping the wavelength in half. So if you look at this nice B, very, very deep, if you chop the string in half, so right in the middle, so right there, then you get a half a wavelength and twice the frequency, which should be an octave up in the exact same note. Same note. And if you chop it in half further, then it goes even more. And you can chop it up even further, and it goes some more. You can't really hear it. That one's kind of hard to hear. It's very harmonic, very high. But I hope that shows you how frequencies are not linearly related to their note names on this scale. I hope you've enjoyed this talk on logarithms and exponentials. Have a good day.